Okay, so I want to talk about two major concepts that often cause a lot of confusion for students, and those are isotopes and ions. And as you can see, we will be modeling isotopes and ions with Skittles. One, because I'm hungry and I ate all the red ones already, and two, that's what the vending machine on campus had that would work. So that's what we're doing, modeling isotopes and ions with Skittles. So to start with, we're going to use boron as an example. So there are two main isotopes of boron, which can be expressed this way, boron 10 and boron 11. This number represents that atomic mass for each of them. So they're both boron. They are the same, iso means same, the same element. They are occupy the same position on the periodic table, which is what this tope means. Same position on the periodic table, different element. Another way that we could express these exact same elements is this way, which is something you've seen in the book, which also further emphasizes that they are the same element. Here we have that mass number, or that atomic mass for this particular particle, listed above, and then the atomic number, which we would get on the periodic table, below. Whether you're presented it this way or this way, you're going to have to be aware of how many protons are in the nucleus, and that number would be here. This is the atomic number listed on both of those, and if you didn't have that kind of format, you'd want to look at the periodic table instead and find it and look at its atomic number. It's a little bit tiny on this particular periodic table, but we have it listed there. So what we're going to do is we are going to try to create a little model of each of these. We're going to do it in these circles, of those three subatomic particles that make up each of these atoms. So we're going to need a key down here at the bottom, because we're going to have protons, we're going to have neutrons, and we're going to have electrons. So because I like alliteration, our protons will be our purple Skittles. It doesn't work for any of the others. Neutrons will be green, and then our electrons will be our orange Skittle there. You can tell this isn't at all to scale, because we know that this particle is actually, nearly 2,000 times bigger, but they don't make Skittles that small nor that large for that to work. So let's start with boron 10. So boron 10, we are going to need 5 purple Skittles, because that's its atomic number. So it has 5 protons in its nucleus, so I'm going to get 5, watch my Skittles, 5 purple Skittles, and that's going to represent the nucleus of my atom. And then I want to do my neutrons next. So the neutrons and the protons together are what make up the mass of the atom. So this number here telling me that the mass of the boron particle is 10 AMU. Because each of those has a mass of 1, it's also the number of protons plus the number of neutrons. So based on that, since I have 5 protons listed here and on the periodic table, I must have 5 neutrons to get this number, this mass number. So I'm going to need 5 green Skittles to represent my neutrons here. Pack them into my nucleus. We'll make it colorful. Woo! There. And then for electrons, atoms are by definition neutral. So if I have 5 positive particles, I must have the exact same number of negative particles to cancel that out. So I need 5 orange electrons. And I'm going to just put them on my circle outside. So that is a Skittle model of a boron 10 particle. It has a mass of 10 AMU because it has 5 of these heavy protons, each having a mass of 1, and 5 of the neutrons. And it has no overall charge because for every one purple, you can see it, there's a match. There's a negative electron. For every purple, I have an orange. So I could kind of line them up so that they show that it cancels out. Now for boron 11, you're going to notice a lot of that process is going to be the exact same. For boron 11, iso means same. The thing that is the same about them is that number of protons. So in boron 11, boron 10, we both have 5 protons. The difference is that boron 11 is just a tiny bit heavier. It's heavier by 1, and that's because it has 1 more of these. So to find the number of neutrons, I'm taking this mass number, which is the sum of the protons and neutrons, and I'm subtracting it from the atomic number, which I found on the periodic table. So 11 minus 5 is 6. So I have 6 neutrons, which I'm going to mix up here to make my nucleus. Now, it doesn't impact the number of electrons I have. This is still a neutral particle. So 1, 2, 3, 4, 5. My boron 11 has an equal number. So each of these has, you can think of like a dance partner. I have a purple for every orange. So those positives are canceled out by the negative. Overall, I have no charge. So overall, you can see these look really similar because the only difference is the number of neutrons in the nucleus. Boron 11 has 1 more neutron than boron 10. In the other areas, it's the same. So an isotope are atoms, or isotopes are atoms of the same element that are different in mass, heavier or lighter, due to this subatomic particle. And they're going to be heavier by 1 AMU for every 1 neutron they have more than the other. And we can express them this way, where we write the chemical name and then its mass number, or we can express them this way, where we have both the mass number and the atomic number for the different ones. Now, if you're looking at this, these look a little bit like the Bohr model, where we have our electrons, or even Rutherford's model, orbiting our nucleus. So where are the electrons really? Where would we really locate them? We can't really model that with skittles because it would get all complicated trying to show areas of probability where the skittle might be found. So I'm going to move this really carefully because we might want to come back to it. But sticking with boron for a second, let's talk about its electron configuration. Because rather than a skittle model, the electron configuration is kind of just the overall way that we would express that, and we would answer that question. Okay, these electrons, since they're not really orbiting, where are they? Well, they're going to be in those different principal energy levels, in their different sublevels, in their different orbitals, in those 3D dimensional spaces that describe that probability of finding an electron. So based on boron's location on the periodic table, its electron configuration would be 1s2. Now I have to go through the second period, the s block. This is my s block. I go over 2. I go through both of them. And then I jump over here to the p block. I'm still in the second period on the periodic table. So my last electron is located in the 2p sublevel. So that's the electron configuration for for boron, whether it's a boron 10 or a boron 11, because remember the electrons aren't different between those two, just the number of neutrons. So another question that we might expect to see on a test or quiz we want to be able to do is then identify, pardon me, I'm trying to move this around a bit. How many valence electrons is this? Well, valence electrons, remember, are the electrons in the highest valence shell. That's the highest principal energy level. So the highest principal energy level here are these 2s. It's not the highest overall sublevel, it's the highest principal energy level, which we call a valence shell. So I can see I have 2 here, and I have 1 here. So that would be 3. And we talked today in class, or we've talked in class, about how we can also use the periodic table by counting the columns, but we skip the transition metals. So 1, 2, skip a few, 3. It's the same number. That's good. That means we're probably doing it right. So how then can boron become stable? Can do it by becoming an ion. I want all this on the screen. Becoming an ion by gaining or losing enough valence electrons to have a full valence shell. Now, in order to fill this valence shell, I would need to gain 5 more electrons to fill this 2p sublevel, which seems a little bit unlikely, right? Instead, if I lose these 3, so by losing 3 electrons, I'm going to end up with an electron configuration of just 1s2. Now that's the same electron configuration as one of our noble gases. So we say the octet rule because most of them have 8, so most elements are seeking 8, but if you're close to helium, if you're closer to helium than to neon, then this is the closest stable noble gas. And so this, when boron loses 3 electrons, it becomes isoelectronic with that noble gas helium. So how does that impact its charge? So let's go back just really briefly to the model. And we don't need to focus on both of them because it is the same, so we'll just focus on one of them. So I'm gonna reorder these a little bit because I can do that with my Skittles. So right now, the way I have these orders, I put the protons on the outside. Now that's not remotely accurate from what happens, but imagine thinking of this as like dance partners. I have a proton, a positive proton, and a negative electron, and I have 1 for each. Everybody has a little dance partner. That means everybody cancels each other out. +1, -1 together is 0. So that would be overall a neutral atom because I have just as many positives, negatives as I have positives. But we just said that boron, if it loses 3, will become more stable. It has a full valence shell and now would be isoelectronic with helium. So here, if I look, I have canceled out, so I have my plus and minus becoming 0, and then I have 3 protons. I didn't gain a proton. These are protons that were already there, but I lost the particle that was canceling them out. So that means I'm going to have a charge of +1, +2, +3. A positive for each one of these positive particles that doesn't have a dance partner, making boron's ion boron +3, as we would predict with its location on the periodic table. It is easier to lose 3 and not have those protons cancel out than it is to gain. So let's look at one more, just again, for just a little extra practice. What about oxygen 17? Let's kind of go through that whole thing again. So, oxygen 17, this is the mass number of this particular isotope of oxygen. There are different isotopes of oxygen. Oxygen atoms come in a slightly different form, heavier or lighter. So this is that mass number. When I look at the periodic table, though, I see that oxygen has 8 protons. That's its atomic number. And depending on where, your periodic table can put that number in different places, but you should be able to find that. So I could write this in the little nuclide form, 17/8. So if I want to model this, I need 8 positively charged protons. So 1, 2, 3, 4, 5, 6, 7, 8. There's my nucleus, or the start of it. Next, I want to figure out how many neutrons I need. So I take that mass number, and I have 17 minus 8, which is 9. So I need 9 neutrons. 2, 3, 4, 5, 6, 7, 8. Whoa, my Skittles are hopping away from me. And there's my little nucleus. And we'll do our little, even though we recognize this isn't the most accurate. So if this is a neutral atom, which I should assume it is because it doesn't say anything to the contrary, then I need a dance partner, or I need a partner for each one of these. I need them to cancel out. +1 minus 1 equals 0. So for every +1, I need a -1. So that's 1, 2, 3, 4, 5, 6, 7, 8. Its atomic number. I need 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So at present, I'm modeling a particle of oxygen 17, one of the isotopes of oxygen. Ignore those side ones. I'll eat those later. So you can see I have 8 electrons. Are all of these valence electrons? No. And that we don't have that modeled. So in order to solve that, we can do 2 things. We can look at the periodic table and do 1, 2, skip a few, and count, and we're going to find that 6 of them are valence electrons. We could also look at its electron configuration. 1s2, 2s2, and then we have 2p4. So our highest valence shell, or our highest principal energy level, is here. So we have 4, 5, 6. So 6 of these are those, we said interesting electrons. They're the ones that make it chemically reactive. And you can see here I have room for 2 more in this sublevel, which helps us understand why oxygen becomes a -2 ion. Because if it can gain 2, that would make it isoelectronic with neon. It would become 1s2, 2s2, 2p6. And then it would be isoelectronic with that nearest noble gas. So let's have it gain 2 electrons. So now I have an imbalance between my pluses and my minuses. We're going to line them up like they're line dancing or something to see that. Everyone that's partnered up is canceled out. My neutrons are neutral, so they don't impact it, so I'm going to leave them in the center. So everybody's canceled out except these 2. So I have 2 negatively charged particles that aren't being canceled out because oxygen gained these. It gained these in order to have a full valence shell and be isoelectronic with neon, which makes it the most stable. Remember, elements and atoms tend to chemically react to be isoelectronic with their nearest noble gas. So because I have 2 particles that aren't canceled out, I am a particle with an overall -2 charge. I hope this cheesy activity doesn't just make you hungry, but reinforces some of those concepts that can be a little bit troubling. Sometimes seeing it in a simpler way, a cheesier way, a way that involves Skittles can help out. If you have any questions, send me an email. See you guys soon.